So this is my third part of review of chapter 17, orthogonal matrices and Gram-Schmidt. So let's begin with the number 4, which is the Gram-Schmidt. So the idea of what it is really important, so let's start with that. So the idea of Gram-Schmidt is how about if we have like a set of just an independent vector. Let's say, I hope these are independent. Okay, and let's name this A, B, and C, and how from them you can come up with the orthogonal vector, and even more the orthonormal ones, because here once you get the orthogonal ones, you can just always divide it by its length, and then you get the unit vector. So following the notation from the book, I'll name this one A, B, C. So the goal is to find the capital A, B, and C, which are the orthogonal or the orthonormal one, from some random independent vectors, set of independent vectors. So how do you do that? So to be more clear, this is what we are going to do, like geometrically. So let's say you have the subspace V, and then let's say the A, the small a here lives in this subspace V. So you got this one. So initially we always start with we set the first vector to be actually the orthogonal one, and then we can just divide the A by its length again to get the unit vector. Okay, and then so we have the Q1, and then let's say you have this B, small b, which is independent, but they're not really orthogonal to A. So we are really interested in this part of B. Let's call this a capital B. So we're interested in this part, which is the one that is orthogonal to the small a, or in this case also the same as A, or the Q1. And what this is actually is what we have been learning so far, that this is actually the error vector, which is here. So if you remember, we have the error vector equal to B minus P, and B, and once again P is the projection matrix, which is the nearest projections of a B, the nearest estimation of B in the subspace of V. But now we care about getting the E, which in this case we will call by the capital B. So that's, I think this is the idea, the whole idea of Gram-Schmidt, and it's really important to understand them. I saw that there are actually two ways that you can compute this. So the first way is actually what you read from book, so I'll discuss that first, and the second one is actually what you watch if you watch the recitations of the lecture. So first, just to remind again, so we have the three set of independent vectors A, B, and C, and then we want to get the capital of capital A, capital B, and capital C. So first, we always set the initial vector to be A, and in this case, remind again, so this is the orthogonal one. Keep in mind they might not be orthonormal, so all you have to do again is divided by its length. So set A to the small a, so we already have our A. Let me square that, and then to get the B, so we need to subtract our initial vector B. So remember, so B is like branching out of, let me try to draw more beautifully. So B is like kind of like branching out somewhere, and this is our capital A already. So B has to be subtracted by some matrix, by some vector in this direction. So we want to get this component, right? We want to get the capital B, so we need to subtract something from B, and that something is that component of B that is projected onto the subspace, which is in this case the P. And I'll just write first the formula that is important to remember. So this is how it goes. And actually, where do you get this? Where does this come from? So this is actually just the P. And if you remember, the P is the some combination of the columns of A with the x hat. So x hat is the new x, remember? And then the x hat itself is the A transpose B. So A transpose B, and then A transpose A. Okay, so this is how you get them. And you might remember, you see also the x hat in this form, like AT A inverse ATB. Well, this is also correct, but remember that when we're working to find the x, the A here is a rectangular matrix. While in this case, the capital big A is actually just a set of one vector, like x, y, z. Okay, so you can actually do this division by this term, because this will be just a scalar value. And then this is because the capital A is just a scalar value, then a scalar divided over scalar. This is just some kind of like a factor multiplier. This is also scalar, and then the scalar times the matrix A. So we can get the capital B. Let me delete those quick. Now let's go for the capital C. Similarly, we can get C by initially subtracting the C part by something. So now there are two components that plays a part. So let me write down the formula first. So now, because we have those two components before, the orthogonal ones, so right now C must be subtracted not only from the result of the projections of the A matrix, but also the projection of the B. So it's like C, which is projected by A, and then component C projected by B onto the subspace where B lives is different. So we need to subtract C by this component and this component. So that's why we get C. And it's pretty structured. I mean, you can follow the formula, the format, and if you get another vector that you need to find the orthogonal form of that vector, that you can follow the same manner. Now let me discuss quickly about the second way. So let's define again the problem. So we start with the independent vectors of A, B, C, but we want to get the orthonormal out of them. So here in a new way, we first compute the Q1, which is simply our A, but we divide it by the length of A, because A is again should be normal in the unit vector. But the Q2 is similarly, we start from B, and then we need to subtract the projected B in a component of A, or Q1, from B. So let me write down for the formula. And then when I see this in the lecture, I kind of wonder, where does this come from? Okay, and I might think that this comes from here. So again, let's start with B, where we define it in terms of A and X hat. and then we remember that in q word that it is simply converted into q, and then we have the x hat is the q transpose b. So we have the q transpose b. So it is translated as the q1, q2, q3, and then this is like the collection of scalar value. You have q transpose b, which is like the dot product of this and this, q2 transpose the dot product of q2 and b, q2 3 b. So actually just to reiterate that this is also similar to q dot product b. Okay, so see, so I think this came from this term right here, the q1 transpose b q, which is equal to this one. So this is again the projection of the vector b into by q1 transpose, or in onto the subspace where q1 and a lives. There's a discussion in the book about how to like separate each component of q1, q2, and q3, so that's why I guess this is where they use it. So q2 again is the vector b minus the component of that b projected in the q1, and we can similarly in the same manner we can do also for q3, which is just the c minus q1 c minus q2 to t c. Okay, so just want to briefly mention about that, because once you watch the recitation you will find the lecturer use this formulation, but I also compute with this one and they result in the same way. They are equivalent. They produce a equal result. So if you have a better source of where does this come from, or if I have a incorrect understanding, feel free to let me know. Thank you.